That's what I should do. Okay. So we've determined that x, y, z represents any point in that plane. And what's the relationship between the two vectors that are up there? They're perpendicular, right? So n just goes straight up. So it's n is the vector perpendicular to what? Not just that line. It's perpendicular to that. Any vector in that plane. Any vector in that plane. Do you agree with it? I'm trying to make sure you understand everything that's going on up there. Is everybody with me so far? Why is it called n? Does anybody know why the vector is called n? There's a name for that type of vector. It's a perpendicular vector. There's another name. There's another way to say perpendicular. It begins with n. Has anybody heard it before? It's fine. Normal. Has anybody heard that before? In physics, right? Probably, right? Yeah. Perpendicular to the acceleration. Yeah. AP Cal. Oh, good. Excellent. So n normal. So you have a normal vector. Now, how many different... Now, does the magnitude of the normal vector matter in this instance? Does this picture say anything about the magnitude of the normal vector? No, it's just the direction of the normal vector is what's important. The direction of the normal vector is what's important. So let's call that normal vector. Let's just call it A, B, C. It has an x, y, and z component. You with me so far? Yay? We're kind of with me? So this A, B, C starts at x naught, y naught, z naught. It goes in that direction, A, B, C. It's a normal vector anywhere in space. That's right. This vector right here, this line segment right here, we'll call it this vector, excuse me, starts here and ends up right here. So that vector, P naught P, what is that going to be equal to in component form? If you had to write the components of that vector, what's the x component? X minus what? X naught. And what's the y component? Y minus what? Y naught. And z minus what? Z naught. These two vectors, what's the relationship between these two vectors, A, B, C, and x naught, y naught, z naught? What's the relationship between those two vectors? It's right there. I've asked you this 3 times. I'm not asking you a new question. I'm just asking you to say it again to drive it home. What's the relationship between those two vectors as described by the picture? They're perpendicular. So last night you were working with what new mechanism? What was that new thing you were working with? What was it called? The dot product. The dot product. If you know that two vectors are perpendicular, what do you know about their dot products?
0.
So you know that n, I'm going a little further here, you know that n dot p naught p, you know that that should equal what? 0. And how do you go about writing the dot product of two vectors? Well, you take the two vectors A, B, C, dot, so you have x minus x naught, y minus y naught, z minus what? Z naught. Right, exactly. And that's going to be equal to what? What's it going to be equal to? 0. Why is it equal to 0? Because the two vectors are what? Perpendicular. Perpendicular means the dot product of the two vectors is 0. So if we actually do this out, what does A get multiplied by? X minus x naught plus what?
B times
Y minus y naught plus c times z minus z naught equals 0. True about ABC. What's the one thing that had to be true about the vector containing ABC in order for this to work? It needed to be a what? It needed to be a normal vector to the plane. What does this therefore represent right here? This is the key thing, the setup for everything. What does this therefore represent? So for example, let's say you gave me a normal vector. Give me a vector. Any vector you want. Numbers. Give me any. Yeah, I like, no, you gave it to me with an arm motion. I like that. Actually, that's pretty good. But let's just say, so an example. Let's just see if you can figure out what you're looking at based on an example. Give me a vector n. Any vector. Just make one up. 1, 2, 3. Nice. You have the vector 1, 2, 3, right? Give me any point in 3 space. Brenna, give me a point. 6, 0, 1. Can you tell me the equation of the plane that passes through the point 6, 0, 1 that is perpendicular to n? Can you? Equals 0. That right there is the equation of the plane that passes through the point 601 that is perpendicular to the vector n. How many pieces of information did we need to write the equation of a line in 2 dimensions? How many pieces of information did we need to write the equation of a line in 2 dimensions? 2. Point and slope. Or if we had 2 points, what could we find? The slope. So point and slope. To find the equation of a plane, you need 2 things. What are the 2 things you need that immediately give you the equation of the plane? Point and any normal vector. So when I say any normal vector, how many different normal vectors are there? There's an infinite number, because did it matter what the magnitude of n was? No. So let's say we change the magnitude of n. We know that this is parallel. Can you give me a vector that that's parallel to? Any vector that that's parallel to. Can you give me one? What? 2, 4, 6, right? What happens to this equation right here? If we use 2, 4, 6 instead of 1, 2, 3, where does the 2, 4, 6 go?
Goes
2, 4, and 6. But then, once we plug in 2, 4, 6, what can we divide everything by? 2. And what do we have? The exact same thing, because what's the number on the right-hand side? 0. 0 divided by anything is still 0. So if you have a normal vector and a point on the plane, what can you find immediately? The equation of the plane. If you have a normal vector of the plane you're looking for and a point on the plane, you can immediately find the equation of a plane. This is the equivalent of point slope form right here. Can you simplify it? Can you multiply things out? Will we do things with these planes? Absolutely. But the key thing to realize is, if you have those 2 pieces of information, you immediately have the equation you're looking for. So let's expand this a little. AX minus AX naught, right? Plus BY minus BY naught, right? Plus CZ minus CZ naught equals what? 0. So you have AX plus BY plus CZ is equal to AX naught plus BY naught plus CZ naught, right? Did our perpendicular vector change at all? Did anything happen to the coefficients? No. This is still what? What is that going to be? That's a what? That's going to be a constant, right? Does adding a constant change anything about the relationship to the perpendicular vector? No. All those is raise and lower the vector. It doesn't change anything about being perpendicular. It doesn't change whether or not it's perpendicular or not. So going back over here, what's the, for number 10, what's the normal vector? 2, 1, negative 1. Okay. So work through 10 through 26. You can work with pairs. I'm going to draw you a picture here. Ready? Here's an arbitrary plane right here. Okay? Everybody sees that right there? Great. I'm going to draw, here's a normal vector for that plane. You with me so far? I'm going to draw another plane that is parallel to that plane, okay? So we'll call this plane P and this plane R, and I'm telling you that P is parallel to R. So the normal vector hits right here, and the normal vector hits that one right there. What other way can you tell if 2 planes are parallel? What's another way you can tell that 2 planes are parallel, given that picture? I'm telling you that plane P is parallel to plane R. N is perpendicular to P. No, I'm not saying not. So prove that what? No, prove what? You don't need to prove it, but if you do prove it, then what is true about the 2 planes? They're parallel. So parallel planes share what? Common normal vector. Parallel planes share common normal vector. So let's look at 19 for a second. If that's 19 right there, can you tell me what's the normal vector for this one? 2, 4, negative 3. And it needs to go through? So exactly. So when it's saying parallel to a plane, it's just giving you the normal vector. Giving you the normal vector. 2 planes are parallel if they have the same normal vector, right? So this plane right here, what's the normal vector for that plane? Right there. That's the normal vector for that plane. So any other plane that's parallel to this one, it could be stacked this way or whatever, right? The same way, it's going to have the same what? Normal vector. So it's going to go through this point with this normal vector. It has to be parallel to this plane. Why? Because it has the same normal vector. If two planes have the same normal vector, they are what? Parallel. If two planes have the same normal vector, they are what? Parallel. So if you write an equation now using that point and that normal vector, do they share normal vectors? Yes, so therefore they must be what? Parallel. So can someone just looking at those numbers tell me what the answer to this question is going to be? 2 times what? X minus 1 plus 4 times y minus 0 plus minus 3. Sorry, I'm writing the wrong number. There's that switch I told you about. Minus 3 times what? Z, not x. Z what? Plus 1 equals 0. This plane, what's the normal vector for that plane? 2, 4, negative 3. What does it pass through? 1, 0, negative 1. Is that parallel to the plane we want it to be parallel to? Yes. Why? Because they share a common normal vector. Exactly. Exactly. These questions, many of them are going to revolve around certain observations like that. And one of those truths is you can prove that two planes are parallel if they share a normal vector. Exactly. What's that relationship we talked about last class? The dot product, do you remember? So it was V1, W1 plus what? V2, W2 plus W3 is equal to what? Cosine theta. That's the phrase you need to memorize, because if you memorize that, can you figure out a whole bunch of stuff from there? Because what is, oh, I memorized that, so therefore theta is going to be cosine inverse of what? V1, W1 plus W3 over what? Yep. The product of the magnitudes, right? Like that. So of the things you can memorize, the best form that I think is going to be most helpful to you is that form right there. What do they call each side of that equation? The dot product. Each side is called a dot product. It's a little confusing. It's a little confusing. How we feel? Well, V dot U, do you remember that statement I told you to memorize? Where was it? Right here? You see this, everybody? What's the right-hand side of that equation called? The dot product. What's the left-hand side called? The dot product. So if you have this, either one of these is V, in this case W, right? I'm sorry, I'll write that in something that you can actually read. V dot W. That's both sides of this, correct? Let's go back down to what we were looking at. What was that key thing I told you right at the beginning of this section that is the key to everything we do today? U is a unit vector, so the direction we're going in is going to be, we're calling it a unit vector. Let me give, it is a unit vector, it's not that we're calling it a unit vector. So look, what can we just arbitrarily add to this expression right here? The what of U? The magnitude of U. If we wanted to, what could I park right there? Why am I allowed to just park the magnitude of U right there? It's 1. You're allowed to multiply by 1 because 1 is the multiplicative identity. It doesn't change anything. But what does this equal? Magnitude of U, magnitude of V, cosine theta. What is that? What is that? That is U dot V, right? That is U dot V. So that's where they get this from. Are you with me so far? But the only reason we were allowed to do that was because the direction we're going in is equal to 1, because U is the magnitude of the direction is 1. It's a unit vector. It's a unit vector. You with me so far? This is a scalar though, right? It's not a what? It's not a vector. If I told you, hey, that's the direction we're going in, and a certain magnitude, can you find out the actual vector representation of the resulting vector? Absolutely. What's the direction we're going in? U. U is the direction we're going in. What's the magnitude of U? 1. If we multiply U times 7, what's the magnitude of the vector become? 7. If we multiply U by 12, what does the magnitude of the vector become? 12. What's the magnitude of this vector? V dot U. What's the magnitude of this vector? V dot U. What direction are we going in? U. But what's the magnitude of U? is 1. This is hard. I'm saying this out loud because it's hard. The magnitude of the direction we're going in is this, but the direction we're going in is u, right? So if we want the actual vector, v parallel, the vector, what is it? It is the magnitude we want in that direction. The magnitude we want in that direction. What's the direction we want to go in? U. What's the magnitude? V dot u. So this represents v dot u times u. That's a scalar times a vector. A scalar times a vector is a vector. But since the magnitude of u is 1, what's the magnitude of this? Well, the magnitude of this is v dot u, which is the magnitude we want it to be. So if you want to know the vector v parallel, all you need to know is u and v, where u is the direction you want to go in as a what? Unit vector. And v, if this is the box we're pulling, is the force vector. Are you with me so far? So if you have them both in vector form, are these force problems pretty easy? Yes. Are you always going to have them in vector form? No. But do you have practice resolving things into components? You do. You absolutely do. So where is this going to come into play? Find the magnet, find that component right there. If this right here, if this is F, so the force of the wind right there, if that's F, find the purple. What do you think that purple is? Problem. And just to reiterate here, we were trying to find how much of that force vector is actually going in the direction we want to go in. And were we able to figure that out? Yeah. How much of that force vector? √3/2. That's how much of that force vector is being translated into forward momentum. You with me? Force vector, and this is a distance vector, right? If they're going in the same direction, it's really easy, right? But are they always going in the same direction? No. So the way you can think about this is W is going to be actually equal to the F parallel. Like this is the amount of F that's actually going in the going in the direction we want it to go in the direction of D. Are you with me so far, everybody? Right? But what is this right here? What's another way to write F parallel? We figured that out all right. What is that? F times what? It's the magnitude F times what? Times the magnitude of the direction we want to go in. Is it D? What is it? What do we think here? Put this on the record. I'm terrible with units when it comes to this field. So you're going to help me with units, okay? Like I'm really, really terrible about like foot-pounds and newtons and stuff like that. My mind just kind of closes down. So can you help me with that? Can you promise me you'll help me with that?